We are jumping straight in today with a paper called Every Token Counts, Generalizing 16M Ultra-Long Context in Large Language Models. And this isn't just about, a better long context. It's really a moonshot. It's about making LLMs finally truly remember.
That mission is absolutely huge. They are efficiently building models that can handle these ultra-long contexts and actually show true generalization. We're talking up to an incredible 16 million tokens.
16M, that's practically a personalized, infinitely growing memory for an AI.
It is. And the technical achievement here is this HSA-UltraLong architecture. It's an 8 billion parameter mixture of experts, or MOE, and it pulls this off using something called Hierarchical Sparse Attention, or HSA.
Okay, so for you listening, here's the 1-minute takeaway. An ultra-long context model really needs 3 things: sparsity, random access flexibility, and, crucially, length generalization.
And HSA delivers on all 3 by acting, well, sort of like a MOE layer. It uses these learned retrieval scores to fuse attention results from selected chunks of text. This makes that whole selection process trainable and efficient.
And the proof is really in the results, right? The model successfully extrapolates its retrieval capability way, way beyond its 32K pre-training context.
Oh, massively. We're talking over 90% accuracy on standard retrieval benchmarks, like Needle-in-a-Haystack, even when you push it all the way out to that full 16 million context length.
This feels like a fundamental shift in knowledge then, instead of cramming everything into static model parameters, which are, a pain to update.
Exactly. This gives you the foundation for future AI agents where knowledge is dynamic. It lives in this instantly retrievable context memory. That is the definition of long-term memory for a machine.
That dynamic memory, that ability for a machine to truly remember, that's the massive hurdle in current large language models. Right now, when we train an LLM, its world knowledge is just statically confined.
It is. And to update it, you have to retrain or fine-tune, which is just incredibly expensive and inflexible.
So what's the core technical problem stopping us?
It's the classic transformer architecture itself. The full attention mechanism scales quadratically with the sequence length. So if you want to double your input lengths, the compute cost goes up by 4 times.
Which means processing sequences longer than, say, 128K tokens just becomes prohibitively expensive?
Utterly prohibitive on any modern hardware. So the goal has to shift from, compressing knowledge into parameters to just efficiently retrieving it from a context memory.
And to make that work, the authors lay out these 3 non-negotiable properties. You mentioned them already: sparsity, random access, and length generalization.
Right. The first is sparsity. We just cannot afford a full attention over millions of tokens. It's not how our own memory works either. We only selectively activate relevant bits. The model has to be selective.
And then there's random access flexibility. So if you're only picking out fragments, you need to be able to jump to any point in that long history quickly and accurately.
And it's not enough to just bolt on a retrieval system. This mechanism has to be intrinsic to the model, optimized end-to-end under the main autoregressive loss.
And the third, which really determines if this is just a cool trick or actually useful in the real world, is length generalization.
Exactly. You can't train a model on 16 million token sequences forever. It's impossible. So the model has to learn how to retrieve information from short sequences and then generalize that skill to contexts it's never ever seen before.
Okay, so if those 3 are the goal, what have people tried before that didn't quite work?
Well, a lot of things. You have recurrent architectures like Mamba or linear attentions. They're efficient, but they compress all past information into a fixed dimensional state vector.
Which creates an information bottleneck.
A huge one. It sacrifices that random access flexibility. It's like trying to summarize a giant book on a single index card.
Yeah.
You just lose the ability to find specific details.
And what about the existing sparse attention methods? Sliding windows, that's been around for a while.
Sliding window attention is fine for local context, but it has a fixed constraint. Anything outside that 4K or 8K window is just gone. It's inaccessible.
Right.
But more importantly, even the more advanced methods like native sparse attention or NSA, they failed the retrieval test.
Because their selection mechanism wasn't optimized end-to-end.
Precisely. They pointed to a study in the paper, Table 1, that shows this really clearly. NSA with Rope E, it drops from 97% retrieval accuracy at 4K context, which is great, down to just 60% at only 64K.
Wow, that's a huge drop.
It is. The model knows it needs to retrieve something, but its mechanism for picking the right chunk is essentially blind.
So it's like having a librarian who's really fast, but never learns from their mistakes. The search algorithm is fixed. It's not guided by whether the book they found actually helped answer the question.
That's a perfect analogy. NSA's selection part doesn't get any meaningful gradients from the main loss function to improve. And that is exactly why hierarchical sparse attention, HSA, is the solution. It forces the joint learning of chunk selection and attention.
Okay, let's unpack HSA then. How does it make that selection learnable? And why the comparison to a mixture of experts layer?
The MOE analogy is, I think, the best way to grasp it. So imagine the entire past sequence is divided into fixed-length chunks, and each chunk has a summary, like a landmark representation.
Okay.
And the current token wants to attend to the most relevant information from this massive history.
And this happens in 3 stages, which mirror that MOE workflow.
Exactly. Stage 1 is retrieval or routing. The current token computes a retrieval score against the landmark representation of every past chunk. Think of this as the MOE router picking its top experts.
So it's selecting the most relevant chunks from the entire history.
Yep. Then stage 2, intra-chunk attention. Once those K chunks are selected, the model performs standard attention, but only within each of those chosen chunks. It's localized, like a token being processed independently by its selected MOE experts.
And then the magic, I'm guessing, is in stage 3, fusion.
That's where it all comes together. Instead of just concatenating the results, the attention outputs from those selected chunks are fused using the initial retrieval scores, which get normalized via softmax.
Ah, so that's the feedback loop.
That's the critical feedback loop. Because those retrieval scores are used as weights in the final output, the gradients can flow directly back through that fusion mechanism right into the selection process. The model learns which chunks give the most useful information.
Which makes the retrieval part of the optimization problem, not just some add-on heuristic. I also saw they mentioned something about stability using query key normalization. Why was that so important?
When you're scaling up to trillions of tokens, the variance in key and query magnitudes can really destabilize the attention scores, especially in these sparse architectures. They found that normalization was, well, absolutely essential to keep HSA stable and trainable through that entire massive pre-training.
And what about positional encoding? They did something unusual there. They used ROP for short context, but no positional encoding for the long context that HSA handles.
Yeah, that's a known thing with rotary positional encoding with ROP. It's fantastic for local relative position info, but it actually hurts the model's ability to extrapolate to longer contexts.
So to get that massive 16M length generalization, they had to ditch it for the global context.
Exactly. It was necessary to mitigate ROP's negative impact.
So let's talk about the full architecture then. HSA-UltraLong. It's an 8B MOE model, but it's really a fusion of 2 things. SYA for local stuff and HSA for the global massive scale retrieval. How do they stack them?
It's a specific stacking approach. The model has L layers. The lower decoder is just standard transformer layers, all using sliding window attention with a pretty big 4K window.
To handle the immediate context.
Right. But the upper decoder is where HSA gets introduced. The upper layers are put into groups. Each group has one layer with both SWA and HSA, and then that's followed by a few layers that are SWA only.
That's a clever hierarchy. It forces the model to use HSA for the long-range stuff, while SWA handles the local conversation flow.
It is. And the big efficiency hack is that they share the KV cache across all the HSA modules. It's derived from the output of a single mid-layer.
Which has to be about memory compression, right?
Purely. Maintaining a separate KV cache for every head in a 16 million token sequence would just destroy your GPU memory. So they distill the context into a shared, compressed, landmark representation.
Now, this all sounds great, but they ran into a big problem they called the Seesaw effect. What was that?
The Seesaw effect is fascinating. They found that if they trained the model from scratch with a large SWA window, like 4K, the SWA just got too good at its job.
It handled all the short-range stuff so well that the HSA mechanism got lazy.
He got lazy. It had zero incentive to learn the difficult task of long-range retrieval, and so length generalization completely failed.
So they had to break the training into 4 separate stages.
Yes, stage 1, warm-up. They used a very short SWA window, only 512 tokens, and combined it with a global HSA that uses a large POPK. And critically, they injected synthetic ruler tasks into the data.
And ruler tasks are designed to force retrieval.
Exactly. They're specifically designed to test the model's ability to find information far back in the context. This first stage forces HSA to learn high retrieval accuracy from day 1.
Okay, then stage 2, pre-training.
Once HSA has its skill, they increase SWA to the full 4K and decrease the HSA top K, making it a truly sparse attention model.
Stage 3 was the long context mid-training. This seems like another key insight.
It's a huge differentiator. They switched to data specifically curated to have long, effective context sequences over 32K. This basically proved to the model that long contexts are a real and important part of the world it needs to understand.
And then finally, annealing and supervised fine-tuning, a very delicate dance to make sure HSA's skills survive all the way to the end.
That precise staging is what let them overcome the seesaw and unlock that generalization.
So let's get to the payoff. They trained up to 32K, but HSA-UltraLong hits near-perfect accuracy all the way out to 16 million tokens. That's a 500x scale-up factor from its training.
It's incredible. It proves that the learned retrieval mechanism actually generalizes. And the paper has 3 key findings that explain why.
The first one is all about the training data itself.
Right. Effective context length matters.
Yeah.
Models trained on standard corpora, even with the 16K window, just saw their retrieval accuracy plummet as context grew. The decisive factor was that mid-training phase on genuinely long data. That's what boosted accuracy to near 100%.
So it's not just the architecture, it's giving the architecture the right signal.
It's the signal. The second finding then reconfirms the SWA HSA seesaw.
The architectural trade-off.
Yes. They showed that using a smaller SW window, just 512 tokens, during that warm-up led to much better HSA extrapolation than a big 4K window. The large SWA just makes things too convenient. It robs HSA the incentive to learn.
And finally, the insight about scaling. They compare the 8B MOE model to a smaller 0.5B dense one.
And this is where it gets interesting. On a simple retrieval task, they were pretty comparable. But on a more complex variable tracking task, the larger MOE model was consistently and significantly better.
So retrieval is only useful if you have a powerful model underneath to actually reason about the retrieved information.
Exactly. You need that joint reasoning and retrieval capability.
And despite all this specialization for long context, it's still competitive on standard benchmarks.
The MOE variant even scored 1.3 points higher on average than a comparable Quen model, despite needing fewer training operations overall. It validates their whole approach.
Okay, let's shift to the engineering side. If this is so good, why isn't it everywhere? The efficiency benchmarks against Flash Attention 3 tell a different story.
They absolutely do. Flash Attention 3, with its custom CODA kernels, is still faster at shorter sequence lengths for both training and inference.
So HSA only gets a real performance win when contexts get truly massive, like beyond 128K tokens.
Right. So if you're an engineer building, say, a typical chatbot where most conversations are short, you wouldn't choose HSA. Not yet.
Why not? What's the overhead?
It's memory access. HSA sparsity means the kernel is managing all these fragmented memory accesses, which adds latency. Flash Attention 3 uses very tight, contiguous memory access. That overhead just dominates at short sequence lengths.
Which brings us right to the open challenges. The Seesaw problem isn't totally solved. They found that fine-tuning on short data can still hurt long-range skill.
Right, because SWA just reasserts its dominance. And there's also a structural constraint. HSA needs a severe 16-to-1 ratio of query heads to key value heads. That's an information bottleneck they need to solve at the kernel level.
And of course, the short sequence inefficiency we just talked about.
Yeah, until those kernel optimizations happen, HSA won't be competitive on the short-range tasks that make up, most real-world applications today.
But despite all that, this feels like a pivotal shift.
It is. The success is about performing attention chunk by chunk and fusing the results with learned, traceable scores. It makes the whole selection mechanism end-to-end learnable. This really is the path forward for models that need massive personalized knowledge stores.
And this leads to a fascinating final thought for you, the engineer or researcher listening to this. Given how incredibly critical the effective context length of the training data was for generalization, especially that mid-training phase, how might we need to fundamentally restructure our pre-training data sets? If these architectural hacks are only as good as the data that forces them to learn, do we need to start thinking about radically different data curricula for these long context models?